everyone, and specifically, let me start by saying thank you to the Chancellor of Covenant University and the entire management of the university for this platform that has always brought us together to do a deep dive into the different theoretical concepts that would empower the student, postgraduate students specifically, in their respective research endeavors. And this is the May edition of the monthly advanced research tutorial. And this is a very special edition. We want to have an adventure, so to say, into one of the flagship technologies when you talk of artificial intelligence and high performance computing, that is federated learning. And we decided to make it a special one, targeting specific students that require postgraduate students and even faculty and researchers from our partner institutions, from Covenant University, from Summit University, from Landmark University, from Afebabalola University, that require this knowledge to push their research work forward. So I want to especially welcome all the nominees from the different institutions and the experts that are in present for this tutorial. This is just the first leg, and we are going to be exploring the fundamentals of federated learning, as well as an overview of the high-performance computing platforms that are available at the FedGen Research Group, at the FedGen Laboratories in Capic Ace. Okay, and by the time we are moving to the second and the third edition of this series, we will be having collaborators from the United States of America. Okay, and they've been able to come up with flagship frameworks for federated learning. And we are hoping that working with them, there will be a transference of skills in terms of how to make use of that particular framework and how to make use of our own HPC infrastructures, as well as connecting with their own, so that the expected research breakthroughs from our respective work can be achieved. So on this note, I welcome everyone. I wish us a very impactful monthly advanced research tutorial. And Dr. Lawa, I think it would be a good idea to do introduction of participants to know where they are nominated from before we commence the proper tutorial. Thank you.
All right, thank you so much, Prof. Thank you. Okay, so as Prof, okay, good evening, everyone. Mr. Abdul Fatai, are you on the call? Can you hear us? Do you have any challenge at all? I can see your chat. Okay, so while we wait for Mr. Abdul Fatai to get back to us, please, if you're on the call, one after the other, kindly unmute yourself. Tell us your name, tell us the institution you're joining from, and maybe your research area. Just in 1 minute, please. I think we should start with Mrs. Amarachi. And yes, please. Kindly unmute yourself. Tell us your name, institution you're joining from, and your research area. Okay, if Mrs. Amarachi is not ready, can we have another person? Please unmute yourself.
Ma?
Yes, sir.
I remain Abdul Fattah Nasir Musa. By name, my research area is MIS, Management Information System and AI.
Okay, sir. Where you your institution, sir?
Aliko Dangote University of Science and Technology, Wudil, Kano State.
All right, you're welcome. Thank you so much, sir. Nice to have you here. Okay. I can see engineer.
Good evening.
Okay. Yeah, good evening, Mr. Dari. Good evening.
My name is Daryl Atobi Manuel from Covenant University. My research area is the development of radio environment mapping, 3D radio environment mapping using physics-informed graph neural network. Thank you.
Okay, thank you, sir. We're waiting for others.
Ogbede Mahe. Oh, sorry. Can I proceed?
Yes, please.
Ogbede Mahe from Afebawala University. My main area is path planning. We are exploring both machine learning and not machine learning methods.
Thank you so much. Thank you for joining us, sir.
Yeah, good evening. Good evening, everyone. My name is Chiloya Dejumoke from Covenant University. My research area is energy optimization data center using federated multi-agent reinforcement learning network. Thank you.
Okay, thank you, Ma. Do we have any other person on the call?
Good evening. Good evening, Ma. Good evening, everyone. My name is Amarachi. Nominated from Covenant University. My research area is energy optimization in data centers using federated remote learning.
Okay. All right. Thank you so much, Ma. I think I can.
Good evening.
Okay. Good evening, sir.
My name is Uche Chukwu, Covenant University. My research area is risk-aware resource allocation and secure communication in multi-cloud networks.
All right. Thank you so much. Thanks for joining us. Okay, I can see, I think there is one more person. I don't
Good evening,
know.
ma'am.
Good evening, Dr. Taufik.
My name is Taufik Abayomi. I'm from Summit University of Research Area, AI, machine learning, deep learning, image processing, and so on and so forth, ma. Thank you.
Thank you so much for joining us. We appreciate. So I can see, pardon me, I don't know if it's Miss or Mr. Temitokwe Abimbola. Can you please unmute yourself and introduce yourself, please?
Good evening, man. Good evening, sirs. Good evening, everyone. Temitope Abimbola from Afebawala University, Ado-Ekiti. So my research area is machine learning. Thank you very much, sirs and ma'ams.
All right. Thank you so much, everyone. Thank you. So I think we can move forward. Prof.
Good evening, Ma.
Okay.
Good evening, everyone.
Dr. John Wedgin is speaking.
Yeah. My name is John Wedgin from Taraba State University, Jalingo. My research area is computer networks, protocol design, and cloud computing. Thank you.
Thank you so much, Dr. John Wedgin. Okay, so I think I should also introduce myself since I think everyone has done that. So good evening, everyone. My name is Comfort Lawal from Covenant University, and my research area is on cloud computing and federated learning. So thank you so much for joining us. Let's move straight to the business of the day. Okay, so today's tutorial is going to be in two parts. Like I said earlier, we're trying to lay foundation for federated learning today. However, before we go into that, we want to bring everyone on board, because while you're doing federated learning or whatever research you're working on, you need computation resources, right? You need a platform to do your research. So we have HPC expert, if I can use that, in the house with us today. She's going to give us an overview of HPC usage, how you can utilize it in your research. So we're not just teaching you the theoretical aspects, how you can make use of available resources. And so good, we have those resources here. All right. So Engineer Mrs. Sweetwilliams.
Thank you, Dr. Lawal.
All right, so she's going to be the first facilitator for today. She's going to give us a overview of HPC usage. You have 1 hour, Ma. Then after that, we just do we have the second part, which is the fundamentals of federated learning. Thank you so much. Engineer Mrs. Sweets, you have the floor, Ma.
Thank you very much. Can you please permit me to share my screen?
Please go ahead.
Can you confirm, please, if you can see my screen?
Yes, we can see your screen.
Okay. Thank you very much I want to thank the House very much for the opportunity again to speak about something I've been very passionate about since we started working with HPC, high performance computing. Very shortly, say in the confines of the time I have, we're going to be looking at an overview of high performance computing. We try to understand the evolution, take a look at the architecture, its applications, and of course, the challenges. And during the course of the lecture, we're going to be looking at the horizon. And I'm very happy to say that the FedGen high performance computing infrastructure will be our use case. Thank you. Okay. As a way of introduction, like I said, we're going to be, this is what we are going to be looking at conclusively. We'll try to understand the evolution, how HPC evolved, the architecture, how it is built, the content, and why HPC. And of course, it's not without challenges. We're going to be looking at the challenges and the future of HPC. Okay, so let me give it a shot. So the HPC paradigm, I want to approach it from this angle. HPC, looking at it beyond the conventional computing. I believe we're all familiar with the conventional computing. So we are starting from the unknown to maybe what we are just getting to know. I would not say it's totally unknown. All right. So the main goal of HPC, if I can put it together in very simple terms, is to solve problems that are too large, that are too complex, and time sensitive for the standard computers, for the everyday computers we are used to having. And if we look at HPC and pull it apart, it's nothing more than using massive data to solve complex problems. Here I've illustrated that we see these three in this chart. We see massive data applied on complex, used to solve complex problems. We'll see my definition of complex problems as we go on, so that we can all define what problems we call complex and which ones, how we rate them. About the end result, will be real-time intelligence, and then it will result in faster discovery. Summarily, or the components that I would say will make up HPC are the 5 we have listed on this slide. That is, basically, when you get to the nitty-gritty of high-performance computing, all of these 5 components must be represented, or else it is not, it's something that's not HPC. However we look at it, all of these 5 components must be represented. Number 1 is massive computational power. It's an ingredient of a high-performance computer. Massive computational power. The second one is parallel processing, and then high-speed networking. Then we have large-scale storage systems. And the 5th one, advanced resource scheduling. Massive computational power. I want to drive this point home. I'll take you to Argonne Lab, Argonne National Laboratory at Illinois. By the time I paint this picture, you will know what I mean, massive computational power. So I want to talk about one of the fastest supercomputers in the world, as it is right now, the Aurora supercomputer. If I say massive computation power, Aurora has this, these are the configurations. I'm going to give you a few of the configurations. Then I'll leave you to yourself to see whether this computation power is massive or not. Aurora, in performance, is said to have 2 exaflops. This means 2 quintillions. That is, it can calculate 10 to the power 18 instructions per second. That's the capacity of 1 million ordinary computers put together. Now that's what I call massive computation power. In size, I took time to put this configuration together to paint this picture very well. In size, Aurora is said to have, remember I mentioned high-speed network. Aurora is said to have 300 miles of optical cabling. It is rated, the distance is rated to be 2 times NBA basketball court. That's 10,000 square feet. Aurora, so they put the weight there. Now Aurora weighs 600 tons, about the size of the world's largest passenger plane. Now this is what I call massive computing power. And as it is too, in terms of, if we can relate with servers, Aurora has 160 racks. And in each rack, it has 64 blades in terms of server. And that we can also relate with as node. We'll get to know what nodes are. Each node has 6 GPUs and 2 CPUs. So in all, Aurora has 60,000 GPU. Now that's what I call massive compute power. I think this one would have painted the picture of high. We're still coming to that, but I want you to see how this all began, how this story we are telling today all evolved. I intend to illustrate this with this S-curve. Early in the 1940s, we had this, at the beginning, the ENIAC, the UNIVAC, driven by, the ENIAC is the first one, which was driven by the military. And then followed this, the UNIVAC, which was the first commercial supercomputer. Up to 1970s and 80s, we started the Cray supercomputer. We started entering supercomputing. Was characterized by vector processing. That is, vector processing simply means using maybe one parameter to process several data, the matrix application. And by the time we're getting to the 1990s, parallel computing starts. We're still going to enumerate and take a look at what we mean parallel computing, because it's very important to establish this background. So we entered already the era of cluster computing, and message passing interface and distributed systems were introduced. And in the current, the modern era now, that's from 2000 to present, we have AI acceleration. The GPUs came, the cloud, the HPC, and then the exascale computing. Now sit where this is the curve. It also now depends. The question is, this curve that has looked as if it has stabilized, I tend to ask myself, this curve now, is it that it's like a climax, or maybe just the beginning of another bend? It depends on what the future unfolds. And something that caught my attention, or something that came to my mind, that in the 1940s to 1960s, this at the beginning of this curve, what if I tell us today that our cell phones, the cell phones that we carry now, are so many times, many times faster and more complicated than the supercomputer that took Apollo 11 to the moon. So really, we look at it, the system is an evolving one, right? So as an approach, this slide is trying to tell us, or opening up or giving voice to the previous one, showing us basically the hardware we find in an HPC, just like we mentioned earlier. If we take a close look at it, we have the front end, that's the login node. The login node provides the user access, and that's like the door through which you submit your jobs. That's like the interface you use to relate. Like there are two fronts, the HPC front and then the user front. The login node serves like an entrance, an interface between the user and the HPC. And we have the compute nodes. That's what we can say is the muscle that is executing these workloads. The compute nodes consist of the CPUs, the GPUs, the memory, and all of that. We have the storage layer. Of course, you can't process this enormous data and not have where to reside for the interactions to go on. So we have the storage layer, shared parallel file systems. Then we have the high-speed interconnect that can be visioned like the nervous system. That's the communication node that relates all of the components of the HPC one to another. It sits on a high-speed interconnect. Ethernet, the InfiniBand, all the advanced ones, the slingshot. Then we have the management network, where, of course, the dashboards, where you monitor the activities, where the administration of the HPC sits. And like I said, immediately we put together as fresh to introduce or to picture, to give you a view of the FedGen HPC. I would like to relate what you have just seen with our own architecture here. Every of those nodes, maybe just take a look, interact with this sketch, and you see and identify all of the components that we have mentioned. And indeed, you would establish that the 3rd gen HPC meets all of these criteria. So the 3rd gen HPC by every standard qualifies to be an HPC cluster. As you can see from the researcher, that's the user going in, we have the storage, shared storage, we have the compute nodes, we have the network, and we have the login node. The login node here and the management node are together. That's why you can't see. And I have a summary of the compute resources. We have on the 3rd gen, we have 5 nodes. The nodes, the nodes are like the computing arms, the way it is structured. These are the names of the nodes. We have five of them, the total CPU core and the memory we have on the 3rd gen. The 3rd gen HPC cluster has a total of 632 cores, and we have a total memory of 1.96 terabytes of RAM. I feel like putting my hands together because I know where we came from, and I'm also excited because I also know where we are going to. So, like I said, talking about parallel processing. Parallel processing is a very critical part when we are talking about HPC. We have put together these slides to make us envision parallelism here. So it could be dividing data across nodes for simultaneous processing. It could also be executing different tasks concurrently on the same data. And the pipeline parallelism is about algorithm, about AI that is executed in layers. So it could be fed in layers. We could structure this hardware processes this, and then the results are aggregated. The enablers of parallelism in HPC are MPI, message passing interface, and then the CUDA by NVIDIA. So we come to the global applications of HPC. We just look at it globally. Try to paint a picture here, but there's an illustration I would like to look at that came to my mind to drive this point home. When we look at HPC, I like to liken it to reading a most complex manual, understanding it, predicting it, and then creating virtual simulations and testing. I like to represent the power of what HPC does and the power of modern innovation. I like to liken it to that because manuals, reading a very complex manual, like if I say, let's take for example, that the human genome has a manual. I see the HPC as maybe reading it as complex as it is, molecule by molecule, understanding it, establishing how it's working, and then the 3rd stage, it does simulation. So that's applied to scientific research. The Human Genome Project is one of the fields that HPC has brought discoveries. I will always refer to the pathogen challenge, that the global crisis, when we had the pathogen challenge, why HPC came in readily handy was that we can identify that as a very complex problem, because the challenge they had was the massive work they had to do. So by HPC made it possible that things that would normally have been done in maybe the list of space of 3 years, HPC, because it could read all those massive data, learn the pattern, and lead to simulations. It was possible to bring out solution. It was possible to discover formulas, compounds, and how they work, and give us solution in maybe a space of 6 months to 1 year. In engineering, HPC too has taken away, we all know, or we can relate with, maybe in car manufacturing or modeling. Instead of doing trials, physical, I remember then back in Peugeot Automobile, they had very big fields where they said they do test driving and all of that. They crash cars in real life just to do tests. But HPC has made it easy to do simulations without destroying, without so much cost. Especially in dimension, science is increasing. We want to ask more questions. We want more drug discovery. We want more energy efficiency. We want better batteries for our phone. HPC has provided a platform for analysis to be done, simulations to be done. So this manual I'm talking about, whether it's reading complex data from the commercial, whether from in the market, whether stock market, whether for weather forecasting, drug discovery, whether simulations of security, HPC has come to power very high applications globally in powering modern innovation. And as time is going on, the power of HPC has been met with AI, big data, and I call this a great convergence, because big data, as they say, is the fuel. Enormous data sets from IoT devices, that scientific instruments, satellites, healthcare systems, very big data. This data is the fuel. I see this data as the fuel, and then AI frameworks, deep learning, generative AI, LLMs, and computer vision models that structure and learn from the data. And of course, we say HPC here is the engine that drives, like the GPU that drives all this convergence and resulting in modern day innovation. So that as we progress, I used to call this an irony, because at first it was that let's take data to the cloud. That was the in thing. We went to the cloud in the likes of accessing immense compute through platforms like AWS, Microsoft Azure, Google Cloud, diverse. Of course, the advantage was there. There was high elasticity. You could scale very easily. and at reduced upfront infrastructure cost. Fine. But then, why, if it's so beautiful, why then again are we talking? Well, as you can see, they are moving from one thick circle, the centralized cloud. To my right, you see labeled the edge, and you have dots, these orange dots, all put together, interconnectivity. So why are we, I used to say to myself, say we went to the cloud. Now the thing, it was, we took data to the cloud. Now we're saying it's too far. So we have come back. So the advent of HPC, we are coming now because centralized method now has its own downside, which bringing data to the edge now is bringing solution to. So the edge, I call it the edge advantage. The edge, bringing back data to the edge, that means closest to the point of processing in a bid to reduce latency and setting a background to what we are talking about. Vital privacy preservation as federated learning, and then instantaneous real-time decision-making. These are the things that power smart cities, healthcare, smart agriculture, and all of that, localized intelligence. So I see HPC as the platform that is bringing this balance, establishing a balance between these two extremities. Traditional HPC, since it came, has, we have variants now. This is the idea this table is bringing to us. There's the traditional on-premise HPC, which is what we have in FedGen. And then emergence too, cloud HPC is beginning to emerge. That's HPC now as a service. There are current trends that we are seeing. And then we have edge HPC integration. It's also a current trend. These are trends that are upcoming after the traditional on-premise HPC. Now we look at the three of them side by side. For if we look from the angle of infrastructure cost, of course, traditional on-premise HPC has high capital expenditure. Initial cost is very heavy. And that of the edge that the cloud HPC has, that's as it is becoming more available now, if HPC as a service, we have variable operational expense, is not as heavy as the traditional, you pay as you go. And then the edge HPC integration, just have distributed infrastructure. It's also, we can also see, if we talk in terms of scalability, how the three of them play, and latency and primary use, we see how the three of them also play. So of course, HPC is not without its challenges. So we look at global roadblocks to its implementation. I would say in FedGen, we have come a long way because we had opportunity to build from the very scratch. So we have, we can relate with all of the challenges, if you ask me. So the first one we already said, infrastructure and cost. If we put together what has gone to building our HPC cluster, I tell you, it's massive. And when we read the configuration, one may tend to spite it, but we look at what has gone into it, you will know that to build and HPC infrastructure is not cheap. All right, so it's a major roadblock because it's not immediately reachable, it's not immediately achievable to everybody. One of also challenge that I would say we have firsthand encountered is that of energy. I believe every one of us on this side of the divide will be able to relate with very well is energy and cooling. I didn't get the cooling part very well until we brought in our H200 GPU. And I saw the kind of heat those machines are generating. How I really, because we're talking about HPC, cooling will always be a component they talk about. But then when we did our installation, and when the H200 is one of the still the most recent GPUs in circulation now. We just, by the grace of God, we're just tidying up the deployments at the FedGen HPC cluster. When that machine was installed, oh no, the kind of thermal energy that it was generating, I was like, So it comes with a challenge of cooling. And energy is a factor that we all talk about because the energy consumption of HPC is massive. So tends to be a roadblock to implementing HPC. Another challenge is the time and bandwidth cost of moving, like we said, whether from, is a cluster, whether from node to node, whether moving it across, it will take time, it will take bandwidth costs to move petabytes of data from one compute node to another. The one that directly affects us in this part of the world is the next one I'm going to talk about, skill shortage. There's a critical lack of specialized talent to operate and program this distributed system. Since we say it's not one of the conventional systems, it's not like the standard computer. It needs expertise. And that's why we appreciate platforms like this, where we can all enter into this world. It's a different ball game. The operating system, how you submit jobs, how you take out the output, put in the right scripts, how to relate the environment is a totally different environment. And since this is just the emergent, the skill set to play in this environment is still lacking. So we still have constraints. Since installation, thank God, we are beginning to get responses. We are having persons that are coming into the play. At FedGen, we are building a community of practitioners. The flavor is beginning to come out. It's becoming beautiful. We have different professionals from different walks of life. As it is now, we have bioinformaticians, we have people, material science, we have chemoinformatics, and it's very beautiful to see all of them play on that field and in their various niches. So learning how the way a bioinformatician uses the HPC is different from the way a material science person would, the way, and even AI, by the grace of God, as like we said, the third gen is our use case. We have been able to, with time, move with time. We have coding hubs where different persons can have learned to do their work, to code, and we have products already. We have already algorithms, large language models, like one of our platform is the AI for CU. We have speech to text, all of those projects that are already, that are products, working products already. We have our documentation. I would implore that you take time to go through the documentation and see, you would learn how to submit jobs, how to bring out all of that. The documentation is very rich. It will be very helpful to us. I want to bring this home again to look at the African landscape. We have, the investment is growing. If we look at the terrain, you can see the players that we have now in Africa. We have activities, we have active nodes in South Africa, Nigeria, Kenya, Egypt, and Rwanda. And we are proud to say that the Nigeria here connotes, or I can say synonymous with Covenant University, because by the grace of God, is like I said, active nodes. The third gen HPC cluster proudly is the one of the active ones now in this part of the world. And we are doing very well. Collaborations are beginning to come. We are becoming more and more visible. Collaborations are coming, which is the essence of this HPC. So there are opportunities. That's the point I'm trying to make. Look at the opportunities that are abound here. AI for economic development, healthcare analytics, like we already, like the bioinformaticians, the materials, the chemoinformaticians, all of them are players in this field. We also are beginning to have collaborations in all of this area, especially academic research. Since the advent of this HPC here in Covenant, we have had so many collaborations. We can see and conclude that is a platform to relate with the world, the advanced world there. Recently, I want to make reference to a program we attended, and they were talking about how trend has changed and how currently, on a global note, that are out there in the advanced world where AI has thrived, they are saying that fine, they have the infrastructure, they have the technology, but data is beginning to fail them. They have identified that there are discoveries that are not global. And what beauty is there if your product is just serving your own community, your own persons? So that means they have noticed a deficiency, they have noticed a loophole. And where are they saying this data is? They are saying this data is in Africa. So it's a crave now that is running in the advanced countries and the advanced world to partner with whoever can or whoever is willing to bring in. Because in Africa here, we can say we have the data. We are still short of technology, we're still short of the skills, we're still short of the advancement. So you see where HPC comes and brings us together. So they are looking for this collaboration, and thank God we are where we are, the point we are now in time. So it's making this collaboration very beautiful. Dr. Lawal already said, as a way now, that's some kind of collaboration. By the time somebody from the Argon Lab is where is housing, this persons came from there, we met and they saw, that's where we gathered this knowledge. So we are looking towards this, the horizon is bright. That's what I'm saying, there are opportunities. So if for this kind of collaborations to be consummated now, the position we are already is already putting us at a vantage point. So, but the kind of challenges we say we have already outlined them in Africa: fragile power infrastructure, Nepal. We are still coming up in this sphere. It's a challenge we have. Also, though we are coming up, we can have inverters, we can have solar, but they are also very capital intensive. So constrained funding, if it were not for fundings, I tell you, the resources required to build this, I don't know. And like I said too, the skill gap is widening. But thank God for platforms like this that we have come together to close this kind of gaps. All right. So for FedGen, as a use case, FedGen represents a forward-looking application of these trends. All of these trends. This in the future, what are we looking at that is coming out from HPC? What are the things we have already talked of? Edge computing, AI, of course, AI. Any sphere now that does not have AI is not emerging. So we are looking forward in the future to see more of AI native supercomputers. That's supercomputers that are purpose-built for big players like NVIDIA, putting GPUs, accelerators, all of them, AI accelerators, putting them together, building them specific for solutions. And like another area we are looking at for emergence, that will emerge in the future is for HPC to become green and sustainable. What do I mean green now? The energy people will understand. Not just that HPC is here, since it has come to stay and is a major drive in innovation. It has to be sustainable. It has to be environmentally friendly. How do we write more efficient programs? How do we build infrastructure that are sustainable? How do we build HPC infrastructure to the kind of software that we write, to the physical infrastructure? How do we make them eco-friendly? How do we make them environmentally friendly? How do we make them green in terms of energy? So we are looking at new frontiers, addressing things in this direction. Quantum computing is an emerging technology, so we are looking that in the future, there will be more harmony. There will be HPC quantum integration. And of course, our topic today, as we advance, new frontiers will be breaking and federated intelligence will be coming in. So this kind of marriage that I talked about, some persons having data, some having technology, and it's going to ride on this federation. So it's a new frontier that we are looking forward to having in HPC. Exascale computing. We're expecting that computing will still scale. because as data is growing, as science is growing, as we the questions we're asking are becoming more complex. So we are looking at HPC scaling, computing power scaling, and of course, we are looking at autonomous infrastructure. We are looking that AI will come up with more ways to drive HPC itself. And for us at FedGen, we represent looking forward to all of these trends, leveraging federated intelligence and edge orchestration to democratize HPC access and to solve localized and real-time challenges. The question now is, the HPC, the technology is available, the infrastructure is there. What is the next problem you want to solve? What is the next problem we are going to be solving? Okay. As a way of trying to draw a conclusion, I would converge my points to saying that high-performance computing is no longer confined to isolated scientific simulations, that is no longer in silos. Maybe you have your own cluster, it's converging. So the future is seamlessly integrating with AI, edge computing, federated learning, distributed intelligence. HPC is fundamentally shaping the next generation of intelligence systems globally. It is the indispensable engine of modern innovation. Thank you very much. So,
wow.
I would,
Can we put our hands together? I don't know if you're going to do it digitally. If you want to unmute so that we can hear the sound of your hands, please, I think we should do that. Well done, well done, well done. Engineer Mrs. Sweetwilliams. I actually didn't expect less. Thank you so much.